think the way it goes is, it goes with the number of times you have to calculate you need to work out you multiply by this number. Sorry, you have the original number and then you subtract it a number of times until you come to a point where the remainder is going to be less than 0. And that number of times is scales with, I guess, the number that you have. So I think it works out, if you have two n-digit numbers, if I go back to that, if you have two n-digit numbers, it goes as n squared, because you have to count, in a sense, each number twice in the sum. I'm not sure how it works out. A lot of this stuff is a bit quite beyond my grasp, but if anyone else has an explanation, then
maybe let's find one example that we can calculate that matrix multiplication. Give a feel what things in sense.
Would you like to?
I don't know how.
I just wanted to say something about the other thing, the quantum computation of the factors. So, I mean, are they still stuck with 15? I mean, basically they did it like 5 or 6 years ago, didn't they?
Yeah. Well,
so are they still stuck there?
Well, I heard a talk recently by which is related to this, and apparently that's the latest figure. They might be moving on to 21 or something. But it's very possible that they still are, but I'm just wondering why. It's taken.
Yeah, as basically they reached 15 like 6 years ago at least, I think.
Okay. Well, I guess it's maybe it's not one of the main objectives of building a computer to go onto a problem like this, and I think there's something else about quantum computing is they're thinking about two different ways of going about it.
Yeah, I mean, I think that's with the molecular ones, but I think even then they were already working on longer chains.
Okay.
But like with more molecules, more qubits. But I don't know, maybe they haven't had exactly that.
Okay.
Have you not done this n complexity thing? Because you did a lot of like computing.
No, I actually don't know much about that. I mean, it's something I encounter quite often, but I don't have an understanding of it.
Alright.
I mean, I have the general idea, but yeah, I mean, I most likely know significantly less than you.
Well, I doubt that's possible, but we'll see. I wish that we had some more computer scientists coming over to this. Maybe they can correct us. But so hopefully you can see that when we try to make this any process into an algorithm, we break it down to the steps, and it scales in some way with this. And it's not straight away obvious as to the way it comes, especially with this thing like with the matrices, where they got this ridiculous fractional power that they work with. But it leads us to the next bit, which is non-deterministic polynomial time. So you have a problem that you've somehow managed to solve, right? But then you want to check that you've got the right answer. Say you wanted to find out Pythagorean triplets. You want to get three numbers that, when you square the first two, they add up to the square of the third. And there are a number of ways of going about this, and there may be a most efficient way. I think one I learned in school was where you pick out one odd number, you square it, you add 1, then you divide by 2 and subtract 1, and then you get all three numbers. That may not be the most efficient way of going about it. But however you go about it, you can always find out whether it's true or not. You can verify it very simply. Even something like Fermat's last theorem, which you might see a little bit later, if they did manage to find, which they haven't, because it was proved conclusively that you can't, a solution to the a to the n, b to the n equals c to the n for n greater than 2. If you could find a solution, it would be considerably easier to verify than it would be to actually find. And these are the type of problems we're talking about. That you can have a very hard problem, but you can verify it in polynomial time. And this is something like prime factorization, where it might be very hard to factorize it, but you can always check by multiplying the two numbers to get the actual number back again. And we have NP complete numbers, which you have the set of problems which are NP, which you can verify in polynomial time. Then you have the subset of which you can actually you can get any other problem in that set to be merged into, so they can be reduced into NP complete problems. So if I were to draw a diagram of this conceptually, you would have the set of NP problems, and then you have a smaller subset here of should be actually meeting NP complete.
And what does actually NP complete mean?
It's essentially you have a problem that it is NP, but it is particularly hard to find a solution to it. But any other problem in NP can be changed in polynomial time to that problem. So you can vary all the
Okay, so
inputs.
what's the definition of NP complete?
That is the
What
definition.
is the definition to it?
Yeah. And the traveling salesman problem is one. I don't know, maybe you have a Polish version of it, because the one I could find that was the original is the 7 bridges of... yeah, that's right.
Yeah. But that used to be in Poland for quite a long time.
Yeah.
Okay. Because now it's
Yeah.
Russia now, isn't it?
Yeah, now it's Russia.
Yeah.
It's kind of very, very odd. But you have to find a Hamiltonian circuit where you have to visit each stop only once around in a group of points, and you have to end up back where you started. And this is an XKCD comic that I found to illustrate it. Okay, so the question I very quickly come to is the P versus NP problem, which is that if you have any problem, like I discussed with the polynomial, with the Pythagorean triplets thing, where you can easily verify the solution, can you find the solution just as easily? And this sounds like a pretty stupid question to ask, because it doesn't seem in our heads to quite make sense. Why would we want this? It would seem obvious that if you can find the solution easily, it's a different task, but mathematicians and computer scientists want to actually definitely know whether this is the case. And it is actually so important that there was a Simpsons cartoon made about this. Homer ends up taking a drug or something and going into a 3D world, escaping from his 2D confines, and he sees all of human knowledge, and you can see creeping off the edge of the board is P equals NP, which is the more interesting outcome of this question. And over here in the back, I don't know if you can see it, there's a pseudo result for Fermat's last theorem, in which they actually those numbers there come very close to being equal, but they're not quite equal. So it's very actually hard to verify that, because you have to crunch it, these numbers to the 12th power. So the implications of this are, if you have something like prime factorization, okay, you can easily find, if P equals NP, if you could easily find solutions to the problem as easily as you could verify them, then things like security, where you have prime numbers being exchanged and multiplied, that would no longer be a secure method of
So you mean there would exist a classical non-quantum algorithm, but it's just unknown?
Yes, that's right. Yeah. But of course, just because it's done in polynomial time, that doesn't necessarily mean that it's going to be very contracted. The solution might take quite a long time in case you can polynomial.
Okay, so it can be completely different than checking it, but just also polynomial.
Yeah, yeah. So if you could check it in maybe n to the 3 steps, then it could be n to the 20 to come up with it, but it would still be polynomial time and not exponential time. And we won't have these people around anymore because every analytical mathematical problem could be encoded in some sense in an algorithm. Well, maybe not every one, but you could try to, if you could verify the solution easily, then you can just as well, get someone to work it out just as easily in polynomial time.
But is it the brute force method that you try all possible solutions in?
No. The thing is, when this comes up is that even if you get p equals np, it doesn't tell you necessarily the most efficient way of finding it. So you still have to find the most efficient way, but it exists. So
Yeah, but so the proof of p equals np doesn't lead to any method of actually finding those answers.
no, unfortunately not. Or fortunately, if you want to think of it as a method of standing in between descents into chaos online.
Yeah, well, I mean, that would be really chaotic.
Well, all these things like RSA security patch,
Yeah.
where you talk to your bank and things like that. They might, or maybe not, if some mastermind hides a supercomputer in his basement and tries to.
But if it encompasses all possible problems, how can you ever come to a conclusion in that statement? In trying to figure out whether p equals to np, if it encompasses all possible problems.
But this is the thing with mathematics, you can talk about things in the general without going into the abstract, without going into the specifics, I guess. It's just the way you can class computability. These P and NP are ways of classing how complex the problem is computationally, and if they can be done that way, then you get a result. And this was something interesting I found on the way. That people thought that it doesn't equal NP, but some people said no just because they felt like it. And this is another interesting thing that I found, which was an analogy with this. So, if P does equal NP, there's no real balance anymore, there's no need to put an effort in. It would be the same as, if you listen to a good piece of music, it would be the same as actually making it. You'd be as bright and as clever as that person. And I did find, this was the most recent attempt at a proof, by this is from HP. I can actually get onto it.
Imagine to leave full screen.
I opened it before, but is it on your other?
Yeah, I mean, I think you will need to leave full screen.
Well, I can't find the. Oh, there we go. It's okay.
Yes, it's here but not there.
We leave full screen.
Go back to that desktop, please.
Okay.
And leave full screen here.
Do you know how to
Escape F11.
We kind of spoiled the surprise bit.
Try out start now, maybe.
Oh no, you can use alt thingy, doesn't it? Because there's a
Well, but release it at some point. We are not